Okay, so we're gonna try and just go through these kind of quickly, and then if you guys have questions at the end, feel free to ask. But last time I didn't actually finish the exam, and I'd like to actually finish it this time, so we're gonna try and finish it. And if you guys want to pester me at the end, we can go ahead and get that pestering done. So, all right, so we're gonna start with this question here. So you start with um, this enzyme helps convert this acid into prostanoids, cool prostaglandin stuff. Don't care. Inflammatory response, number of different anti-inflammatory drugs. Exhibits Michaelis-Menten kinetics, which is important because otherwise we can't use Michaelis-Menten on it. And we've got the uninhibited state and the presence of the inhibited state. So, and we also have information about the inhibitors. So Y binds non-covalently to the active site of the enzyme, and there's curves for two concentrations of Y. So immediately I'm thinking here this is active site, it's going to be competitive, so I'll go ahead and write that down. You got a competitive inhibitor there, and there's two curves, so I should see a Km increase for two different curves. So I should see an increase in Km for two of these curves. And then I've got Z, which binds non-covalently to another site on the enzyme, but only when substrate is bound to the active site. So it's going to be this kind of ESI complex, enzyme substrate inhibitor complex, and that would be an uncompetitive inhibitor, right? And I would expect to see a decrease in Km and a decrease in Vmax, right? So this is going to be uncompetitive, right? And based off of that, I should be able to come over to this curve and, make some kind of inferences of what I should expect. So this thing says I have two concentrations of inhibitor Y, and inhibitor Y was a competitive, right? And so I'm expecting to see an increase in Km for two of these curves here. So if we look at this graph, right, it says that um, the concentration of the enzyme is 100 nanomolar, and then we've got a 10 micromolar per second Vmax. And the only ones here that even could possibly reach that are A, B, and D, right? And based off of just how this graph is set up, it looks like A is going to be my wild type, right? Just because it's got the Vmax depicted in this question, right? And two, it's got the lowest Km without any effect on Vmax, right? So that's what I'm looking for when I'm looking at these graphs, right? And if we're looking for competitive, right, we're expecting to see an increase in Km. And there's two of the graphs that have an increase in Km. And if I look carefully here, the ones that I see have an increase are welcome. The ones that I see that have an increase are B, right? So B has an increase in Km, and so does D. And C is the odd one out with a decrease. It basically chops the Vmax in half, right? So already I know that's probably my uncompetitive inhibitor, right? But then if I also look at the Km, if it's going to be around 5, I'm looking for where the Vmax is around 2.5, right? And that's probably, I don't know, around here somewhere. And that would be a little bit less than A, B, or D, right? So I'm expecting this to be my uncompetitive. Any questions about that graph analysis? No? And we can see all this okay, right? Yeah, okay. I guess I'll try and zoom a little bit. But cool, right? So based off of that, right, we've got a lot of information, right, on what we can expect for these. So what is the Km for the enzyme in the absence of the inhibitor, right? Show your work, explain your answer, right? So for these, there are ways I'm sure that you could do this with some math, but I think the easy way to go through this is just say um, the Km is the point at which we've reached 1/2 Vmax, the substrate concentration at which we've reached 1/2 Vmax, and we decided that based off this curve, that curve A is going to be our wild type enzyme, and so based off of that, we just got to look at the point at which we get to 5 micromolar per second, right? Because the um, max is 10, right? And the Km is 1/2 Vmax for the substrate concentration, right? So if we look at this, 10 is up here. Where is 5? 5 is around here, right? That probably looked in this red actually. 5 is here, right? And if 5 is there, then we're looking at the concentration there, and it's around 10 micromolar, right? Or sorry, 10? 2 micromolar. It's around 2 micromolar, so we're going to say it's 2 micromolar. And you can kind of explain this by saying, since this is a competitive inhibitor, and Km is defined by as the substrate concentration when 1/2 Emax is reached. That point on like line A or curve A, whatever, is 2 micromolar. Something like that, right? That makes sense? Yep.
So you said that curve A is competitive?
Yeah. So curve A would be. Oh, sorry. Did I mess this up? Sorry. Curve A would be the wild type, right? Curve A is, and the question's asking about wild type, right? Does that make sense? Does that make sense? How I came to that conclusion that curve A is the wild type one there?
So then why an explanation you put?
Did I put competitive? Thank you. You're all good. Probably good that you catch this before I make a mistake. You honestly just have to put Cam as the finest substrate concentration, right? I was thinking about the next question, which is not what we're answering. But yeah, you're right. Cool. Any other questions about that, or any other things that I made a mistake on? Because I might have made a mistake on it again, but all good there. This question, these couple questions here, like these first three, should be kind of quick. It's the last one that takes a bit of time, but so yeah, we'll go ahead and move on to part B. Part B and part C are actually relatively simple. So what kind of inhibitor is Y? It binds non-covalently to the active site. Binding to the active site, it's competitive, right? And we can say competitive. And why is it competitive? It's because it binds to the active site of the enzyme, right? Which is something that mainly competitive inhibitors do. There are cases of like mixed inhibitors, right? But if there's a mixed inhibitor, and I don't know if you guys, I think you guys did talk a little bit about mixed inhibitors, but you generally are not tested on mixed inhibitors because they're a little bit too complicated and they can do all sorts of wonky things. And also, if it was a mixed inhibitor, I would expect to see some change in Vmax as well, right? I need to see a change in both, but I'm not seeing a change in both, so I'm just seeing um, I just see a change in Km, right? And so what type of inhibitor is Z? If we look at up here, Z binds non-covalently to another site of the enzyme when the substrate is bound to the active site. So we're looking at that enzyme substrate inhibitor complex, right? Because it's binding to that intermediate where the enzyme and substrate are bound together, it's going to be an uncompetitive inhibitor. And that's how I can explain that. So uncompetitive because it is binding to the ESI complex or the enzyme substrate inhibitor complex, right? And that's really all you need for these questions, right? Should be some relatively free couple points, right? You again, like I said, you want to spend more time on the math that comes a little bit later. Okay. For question for part D, right? The dissociation constant for Ki for identify the curve for the assay when that. So right, so that this one you have to do a little bit of math, if I'm not mistaken. Yeah. So this one's just a little bit of math. So basically, right, you guys have your alpha equation, right? And I'm just gonna write A for alpha just to make it easy on myself, but I don't have these equations memorized anymore like I used to, so we're gonna have to use this. So it's gonna be 1 plus the concentration of inhibitor divided by Ki, right? And at this point, you're just going to be substituting things in. So I know that inhibitor Y, right, is going to be a competitive inhibitor, right? So I'm only going to see a change in Km, and the change in Km is going to be increase or decrease for a competitive inhibitor. Increase, right? So I should expect to see an increase in Km, right, by a factor of alpha, right? If I was looking at the uncompetitive, I'd expect to see a decrease in Km and Vmax by a factor of alpha, but I'm looking at the competitive inhibitor here, right? So I'm looking for an increase in Km, right? So whatever this A value is, this alpha value is, right, is going to be multiplied by the wild type Km, right, to give me the new Km of this inhibited enzyme with Y, and I have to match that to either B or D, right? Because B and D are my competitive inhibitors, right? Does that make sense? Okay. So if we do our math here, right? Alpha equals 1, and you ideally you write out everything you're doing, because otherwise it'll just be rude and just say no, you didn't write it all out. So write it out, right? It just saves you time and saves you points. So the concentration of inhibitor is 4, right? 4 micromolar. I'm not going to write out the units, but again, make sure you write out the units on your actual test. And then for the Ki, it's going to be 1, right? And you'll know that if you get the answer right, because the numbers are usually quite nice. So if we just do 4 divided by 1, it's 4. 1 plus 4 is 5, so A equals 5, right? And now we have to do the part where we have to multiply alpha by the Km of the wild type enzyme, right? So the wild type enzyme has a Km of 2, right? And so we got to multiply 2 by 5. I guess I'll write some by 5, and 5 is just alpha. Alpha is just a factor, right? There's no units on alpha, right? Which is going to be equal to 10 micromolar, right? So now I am looking for a curve that has a Km at 10 micromolar, and the only one that has that is curve D, right? Does that make sense?
So we're calculating everything in reference to the log.
Yes. Everything. So when you do alpha, right? Alpha is basically a modifier with comparison with respect to the wild type enzyme, right? So whenever you see a question about how is this under competitive or uncompetitive inhibition, right? You're taking the Vmax of the wild type or the Km of the wild type and then multiplying or dividing by a factor of alpha, right? Any questions on that? Okay. Now, if we go on here, stuff's all over the place. Okay, so best completes each statement. Okay, so we're trying to figure out what is true here. So at substrate 6 micromolar, ES is higher, lower, the same in the absence of inhibitor compared to the presence of the inhibitor corresponding to curve B. So if we look at curve B, and we're looking at 6, right, micromolar, here, right? And we're trying to see if in the absence of the inhibitor, how is it going to be compared to the presence of the inhibitor, right? So if we're without the inhibitor, right, we're basically looking at curve A, right? And then if we're with the inhibitor, we're looking at curve B, right? And so if we look at position 6, right, or at 6 micromolar for both B and A, right, you can see that at this point up here, we've reached a higher proportion of Vmax, right? And if we've reached a higher proportion of Vmax, what that means is, generally speaking, we've got more of that enzyme substrate complex forming, right? As opposed to the competitive, right, where we're taking up some of that enzyme with that inhibitor, right? Does that make sense? This is more of an intuitive question. You can't really math this one out, in my opinion. I'm sure you could in some way, but I think it's easier to think about it in that sense. Does that make sense? Yeah? Okay, well, and of course, we'll come back to the end if you guys have questions, right? And I'm here afterwards as well. So And I also have to make sure I read the question correctly, right? Because sometimes they mix around the wording and it throws me off. So is higher, right, in the absence of the inhibitor compared to the presence of the inhibitor corresponding to curve B, right? Sometimes they'll flip the wording around. They'll ask you like curve B with respect, like in curve B before the wild type, right? So he's going to make sure you're reading it carefully. So if we look at the presence of the inhibitor, doubling the enzyme would cause Vmax to increase, decrease, or stay the same. Okay, so this one you can theoretically use an equation for, right? So no matter what kind of inhibitor I use, right, I know that Vmax is going to increase. And I can say that because of this equation here. Kcat times the enzyme concentration, right? That is it, right? There's no if, thens, or buts about it, right? The Vmax will increase because I'm increasing enzyme concentration, right? Now, there is going to, obviously, it's not going to be the max, like the maximum Vmax, right? If I didn't have the inhibitor available, because when I add the inhibitor, right, of course, I'm going to have a decrease in Vmax, right? But it's still going to be an increase in Vmax with respect to the previous one, right? Because before we had 100, I don't know, 100 nanomolar of enzyme, right? But now we add 200, right? So Vmax will go up, right? Even though it's not double the amount as it was before, right? So I would say this is an increase. Good? Okay. So now we're on to question F, right? And we're going to be talking about catalytic efficiency of the enzyme in the presence of the inhibitor. Who remembers what catalytic efficiency stands for? What's the equation for catalytic efficiency? Kcat over Km, right? So the main mistake people make here is they just solve for Kcat. No. You got to solve for both, right? So Kcat over Km, right? Right. So we're specifically looking at Kcat over Km for curve C, and curve C is the uncompetitive inhibitor, right? And this is important because we got to make sure that we're doing the correct math. So the way that we have to solve it, we have to solve for Kcat first, right? And Km is pretty much given here. You kind of have to do a little bit of inferring based off of this graph, right? But generally speaking, it shouldn't be that bad. So I guess we'll start by looking at Km, right? So we know that Vmax is going to be at around 5, right? So we're looking for the point at which Vmax is 2.5, right? And 2.5, this mark here is going to be around 3, right? So we're looking at this mark here for 2.5, right? And for me, seems like it's about 1, right? So we're just going to go with 1. And generally speaking, they should be a little bit lenient with like plus or minus like a little bit, but this one is kind of like right there for you. It's like kind of obviously 1, right? And usually they will make it so the graphs are easy to read like that, right? So we can say that the Km is equal to 1 micromolar, right? That's the first thing we can pick from that. Now, if we look for Kcat, right? Kcat is going to be solved by using this equation here. Actually, it's going to be solved using this equation, right? But we have to rearrange that, right? Because you can't just solve for it like the way it is. So if we rearrange that, right, we get Vmax divided by the enzyme concentration equals Kcat. And does that make sense how I got there? All I did was I divided both sides by the enzyme concentration. That makes sense? Right? Okay, cool. So now we just have to figure out what our numbers are, right? So Vmax is just going to be the 5 micromolar per second, right? So I'm not going to change much there. And actually this time I will put units because I want to reiterate something very important here, right? This is actually kind of weird. Micromolar per second, right? And if we do that, the other thing that we have to look at is the enzyme concentration. And they give you the enzyme concentration here, right, as 100 nanomolar. Or nanomolar, right? However, that's a nanomole, we need to convert it into micromoles. Or you can do it the other way around. You can convert the micromolar into nanomolar, but why would you do that? That basically makes it by a factor of 1,000, right? And I don't like working with bigger numbers. I prefer working with smaller numbers, right? So if we convert 100 nanomolar, right, into micromolar, right, it should be around 0.1 micromolar. Yeah? Are we okay with those conversions? These conversions are really important on the actual exam, and does that make sense how we're doing that? So if 1,000 nanomolars, right, is 1 micromolar, right, we're basically moving the decimal place just one to the left, right? So we're now, instead of at 1 micromolar, we're at 0.1 micromolar, right? That's all I'm doing there. So with that in mind, right, we have 0.1 micromolar, right? And here you just got to do a little bit of math, right? And if you do that, you'll just so if for every 1 unit has 10 0.1s in it, right? So 10 times 0.1 is 1, right? And if there's 5 of these, it would just be 50, right? So we're going to be 50 over S is now our unit, basically. So 50 seconds -1, or whatever you want to do with it, right? Please write your units. That tends to be quite important. But we're not done yet, right? So now we've got, oh God, now we've got this value and this value, right? So now we have to do what we talked about, which is find caloric efficiency, which is kcat over km. This, right? And if we do kcat over km, right, kcat is going to be the 50 per second, right? And it's going to be divided by the 1 micromolar, right? And that's just going to be equal to 50, right? And then for the units, you have to make sure you do the units. So this would actually technically be 50 divided by seconds times micromolar, if I'm not mistaken. Yep. Does that make sense? Yeah? It'll take a pause here because it's going a little bit quick here. But does that make sense for everybody where that all checks out? Give everybody some time to write here. Okay. This is the hard one. And honestly, when I took this exam, I actually tried to do this and I actually realized that it was really hard and I actually skipped and went to do the other stuff and then came back to it. So if you see something weird like this and it requires you to do like 8 different like combinations and plugging in variables and other variables, feel free to skip it and come back to it, right? It's not worth wasting 20 minutes of your time. You only have 45 minutes. You might as well spend the time on other things, right? So, and there's much easier problems here, actually, funny enough. There's so much easier questions that if you go down here, that I would totally recommend skipping that if you're not too comfortable with the Michaelis-Menten stuff. And even if you are, this is a time cruncher and it takes a lot of time. So prioritize the easier questions, get the free points, and then come back and do this later, right? It's only 6 points, right? So, this question is kind of separate, right, from the rest of it. It tells you it's not related to cyclooxygenase, right? So that's the first thing, or the graph shown above. So you can kind of ignore all of that, right? We've got a separate enzyme here that follows Michaelis-Menten kinetics with a kcat of 12, right? So 12 per second, right? In a reaction using 0.1 micromolar of enzyme and 100 micromolar of substrate. Okay, cool. So I've got a decent amount of numbers to work with, right? And you measure the initial velocity as 1 micromolar per second. Okay, so that's a pretty easy number to work with, right? If you perform a similar experiment but change the substrate concentration, calculate the corresponding initial velocity. Okay, so if I'm thinking about initial velocity, there is this equation sheet here. Yeah, so I'm thinking about this equation, right? So that's the only equation I know that calculates initial velocity without any sort of modifiers. And obviously you've got the V naught here, right, with the alphas, but there's no alphas involved in this, right? So I'm looking at this equation. So if I go back up to that question, without me forgetting what the equation is, I'm going to write that V naught or V0 equals V max, right, times the substrate concentration divided by, in parentheses, Km plus the substrate concentration, right?
Is alpha like not affecting it?
No, because there's no inhibitor here, right? Inhibitors are not mentioned here, and even if alpha was in there, alpha is just 1, right? Because there's no inhibitors involved, right? Alpha is only incorporated if they specifically mention an inhibitor. If they mention an inhibitor, then you have to use alpha, right? But this problem is already multi-layered enough that I don't expect them to do something where they add an alpha there. Could they? Sure, but I don't think they would. I think that's too time consuming. Um, but anyway, so we need this equation, right? And the issue here is, right, that so um we can calculate our Vmax really easily, right? We have the concentration of enzyme and we have the kcat. So that's not hard to do. So why don't we do that? Let's start with that. So Vmax, right? Vmax equals kcat times substrate concentration, or enzyme concentration, not substrate. And we can just substitute our numbers in, right? So Vmax equals kcat, so 12. And I'm not going to incorporate the units in here, but please make sure you write them on the actual exam. I just feel like it gets a little bit too messy on these. So Vmax equals 12, right, times 0.1 micromolar. And remember, if you're going to use micromolar, you got to convert everything into micromolar. Or if you're going to use nanomolar, convert everything into nanomolar, right? Just make sure that you're doing that. So if we do this, right, do this math, Vmax is just going to equal to 1.2, right? And Vmax, in that case, is going to be micromolar per second. I will write the units there so that we make sure we get the right units at the end. Right? So we have our Vmax, right? So we can basically say that we've got this, right? Now, the only thing that we're missing, right, is our Km, right? So we don't know what our Km is, right? And we're trying to figure out what the concentration is at, or what the velocity is at 10 micromolars, right? So we have our Vmax, right? We are given a new substrate, right? But we're going to use the old substrate to calculate the Km, right? So we know our V naught of the 100 micromolar substrate, and we don't know the Km. We do know the substrate. We do know the substrate because we're using this 100 micromolar one, right? So we're just going to plug values in and solve, right? And if we plug values in and solve, right, you're going to get something like this. So V naught is going to be equal to 1, right? Because I'm grabbing it from up here, remember, right? If it's going to be 1 there, it's going to be equal to V max, which we just calculated as 1.2 micromolar per second, right? The substrate concentration, right, was 100, right? And then we're dividing this, right, by Km plus 100, right? Probably should I'm actually going to remove these brackets here to try and make it a little bit easier. I'll keep it for, right? Good so far, right? Okay, so now if we do a little bit more math, right, we got to do a little bit of isolation here to try and get Km on its own, right? So the way that we do that, right, is that as this stands right now, right, we're basically dividing both sides by Km. If we multiply both sides by this Km plus 100 term, right, you're basically going to have Km on one side with plus 100 and the 1.2 times 100 on the other side. So if we do it like this, right, it's going to be Km plus 100 equals 1.2 times 100. Are we seeing how I got that? Right? All I'm doing is I'm multiplying both sides by the Km plus 100. Right? So now, right, all I have to do is just do a little bit of solving, right? So I know that Km plus 100 equals 1.2 times 100, which is 120, right? And then all I have to do now is just isolate that Km. So Km is going to equal to 120 minus 100. And remember, these are in micromolar, right? So Km is going to equal 20 micromolar, right? So I've solved for Km now, right? All I got to do now is plug this stuff back into the V naught equation, right? Into this equation here, right? And solve for the new V naught, right? Does that make sense? All right, let's go ahead and do that. So V max, right, I know is going to be the 1.2 that I solved for before, right, times the new substrate concentration, and it's already in micromolar from I don't have to convert anything, right, times 10, right? And then I have to divide all this, that's red, just divide all of this, right, by the Km plus substrate, which is 20 plus 10. Right?
I said 10 again.
So it's 10, right? Because we're using this new substrate concentration.
Oh, and then when we were calculating it,
we used the old one. Yep. Because we knew what the V naught was for that old one. We have no idea what the V naught is for this new one, right? We're trying to figure that out. Right. But the Km of an enzyme is constant, it doesn't change. Unless you got an inhibitor, but there's no inhibitors in here, right? So because we're using an enzyme, no inhibition, right? We just stick with what we know, and we know it's not inhibited, so the Km has to be the same regardless of what I'm doing, right? So now if I solve this math, right, I get a good old, I realized I had to turn that, whatever. 12 divided by 30, right? Which is a bit of a weird number, right? But we can simplify that, right? So this is where your knowledge of fractions comes into play, right? And remember what our units are here, right? We're still doing V naught, right? So we're in micromolar per second, right? So if we just do a little bit of simplification here, right? We can divide both of these by 3, right? You can do 6 as well if you want, but I would say do it divided by 3 because you can get 12 divided by 3 is 4, and 30 divided by 3 is 10, and you know what 4/10 is, it's just going to be 0.4, right? You could totally divide it by 6, right? You could do 2/5 as well, right? 2/5, it's the same thing, it doesn't matter, right? So 4/10, 2/5, right? You know what the answer to that is, that's going to be 0.4, right? So 0.4 micromolar per second, right? Make sense? Yep. Okay. Now we move on to a little bit of enzyme catalysis. And the rest of this is, we'll see. Anyways, if we look at enzyme catalysis, right, we're going to look at this and we're going to say tyrosine phosphatase, right? There are a group of enzymes that remove phosphate groups. Okay, sure. Phosphorylated tyrosines. Okay. They help regulate phosphorylation states of many. Cool. They're giving me a bunch of background, right? Don't really care all that much, right? I'm looking for what the punchline is for this question, right? Active site of tyrosine is diagram below, showing the reaction mechanism depicted. Okay, so we've got a cysteine and an aspartate. So I know from my understanding of amino acids that cysteine, right, pK of around, I don't know, like 8 or something like that, right? Usually cysteine acts as a nucleophile, right? Or a disulfide bond formation or whatever, right? And aspartate is usually acidic, right? So I'm expecting some sort of proton donation, acidic thing with a nucleophile in there somewhere with cysteine, right? And there's a glutamine residue. Okay, not really sure what the glutamine's doing, probably acting as a hydrogen bonder or something like that. And we have a gray circle. Okay, so I know that this thing is involved with phosphate transfers, like phosphates, right? Phosphates are negatively charged, so maybe I'm expecting something to do with the phosphate binding. I'm not too sure, but we'll take a look at it as we go down. Here we have the mechanism. The mechanism is relatively straightforward, right? You just got to follow the arrows, right? The arrows can be kind of intimidating, but all we're doing, right, is we're taking this cysteine's electron pair, right, and then we're attacking this phosphate, right? And then this tyrosine is grabbing this H and then leaving, right? And so we see the substrate is leaving, right? And then that just leaves us with a phosphate, right? And we're just going this way and doing all that, right? So this is one of those questions where maybe I would say it's probably okay to just use the questions to guide what you're looking for, right? So for reaction mechanisms driven by what is the reaction mechanism for this enzyme? And it's to identify all that are apply. I will say now, generally speaking, it's not always true, right? If they put things in multiples of 2, usually there are multiple answers for this kind of question. Is that always true? No, but you should be aware of it, right? It's very possible that they're looking for 2 answers here, and I believe they're looking for 2 answers in this, right? So if we look at the question, right, and we look at the kind of mechanism we have here, we can see that, one, we for sure have a covalent catalysis, right? So this cysteine, right, is forming a covalent bond, right? So I can already say there's a covalent mechanism going on here, right? If it was just an acid-base mechanism, right, there's no covalent stuff going on, right? I wouldn't expect to see a bond forming between the enzyme and the substrate. Does that make sense?
That's basic. Oh.
Yeah, so like for something like acid base, right, I would not expect to see the enzyme forming a covalent bond with my substrate. That is only for covalent catalysis. However, an enzyme can be both at the same time, right? So just because it's covalent catalysis does not mean it's not acid base, right? It's probably both, right? So in this case, I know there's a covalent catalysis going on, right? Because cysteine is forming a covalent bond with the substrate, with the phosphate group, right? If I did not see this, right, it's not covalent catalysis, right? But because I am seeing that, right, it's covalent catalysis. So we can say for sure that one of the things that's going on here is covalent. Now, I spoke earlier, right, about how there is an aspartate in the active site. Now, generally speaking, and you can usually take this as gospel, if they incorporate an aspartate, a glutamate, a lysine, an arginine, usually there's some sort of acid-base catalysis going on. Usually. Is it always true? No, because there's obviously exceptions, right? But you can make an inference based off what you see in the passage, right? And you can say, okay, there's probably some sort of acid base going on here, right? And we can, in fact, confirm there's acid base going on here if we look at this, right? So in this step here, aspartate has its OH, right? And we can see that the phosphate is actually, or this tyrosine is actually ripping off the OH. So aspartate is actually acting as an acid in this situation, right? Does that make sense? In step one, right? So in step one, I guess like step one going to step two or whatever, right? Yeah. But basically, right, we see this here. That is what I'm seeing. I also am seeing this as well, where I see aspartate is grabbing back the H, right? So it is acting as an acid in the first step and then acting as a base in the second or third step, whatever, right? So I'm going to say that it's both covalent catalysis and acid-base catalysis. You theoretically could say hydrolysis, but that's not exactly an enzyme mechanism in this case, right? I think usually when they refer to enzyme mechanism, you're looking at covalent catalysis, acid base, and then I'm trying to think, would they ever make you do like water as like a thing? So I would say no in this case because if I'm looking at hydrolysis and I can see them actually putting hydrolysis as an option, but I would say this is not hydrolysis because I would expect to see the water actually helping with like the breakage of this bond, right? So like the breakage of this bond right here, I would expect to see the water doing that hydrolysis, right? That to me is a hydrolysis reaction, right? Where I'm using water to break a bond between substrates. Does that make sense? So like if I'm breaking a peptide bond, for example, right? I'm using water to break the protein apart, right? That's not what this is doing. The water here is just being used to reset the enzyme to its previous state, right? Does that make sense? Right? So that's where I would make the differentiation there, right? Yep.
So if you see like any kind of covalent bond, it's being covalent catalysis.
Yes, if it's a covalent bond, it's covalent catalysis, right? Yeah, that just period. There's no if thens or buts about that, right? So
What is the covalent bond?
this guy shows up late, and then he's like, "Where's the covalent bond?" The covalent bond is here. Cysteine attacking here.
Also.
Yep. Okay. So circle the answer. Okay, with parentheses. Okay, cool. So this is just a straightforward. Is it a nucleophile? Is it an acid? Is it a base? Cool. Great. We've already kind of talked about this, right? I expect cysteine to act as a nucleophile, and it did act as a nucleophile, right? It's just doing a bunch of attacking. I expect aspartate to act as an acid or a base, right? So cysteine in step one, right? So step one, and they've kind of made this really poor in how they've designed this because they should have. I would specify this on the exam a little bit more, but is what it is. So step one, right? Cysteine is acting as a what? So it's acting as a nucleophile here, right? We're using electrons to attack this phosphate. So I can say this is a nucleophile and move on pretty confidently, right? Aspartate in step one is acting as a what? So aspartate here is donating an H, right? So it's acting as an acid, right? Acid. And then if you look at step two, now it's acting as a base, right? So I want to make this clear. Just because aspartate is an acidic amino acid does not mean it cannot act as a base. It can still act as a base, right? So aspartate here is still acting as a base, right? So we're going to pick this here and say it's a base, and we're going to move on, right? Pretty confident with these answers, right? If you have some OChem, like if you remember some OChem, right, you should be able to get these and you should move on, be confident in yourself, and all good. Now, if we look at these, right, the reaction mechanism shows it proceeds at a neutral pH, right? Okay, so we have a neutral pH reaction, right? Side chain pKr values are so at physiological pH, right? So normally, right, normally it is cysteine is 8.1 and aspartate 3.71. Normally, right? Not in the enzyme, right? If I just had a free-floating cysteine or a free-floating aspartate, that's what they would be, but we're not doing that, right? We have some extra things going on, and proteins change the pKrs of a lot of these amino acids, right? So a little bit different, right? So the pKr for cysteine within the active site, right? So I know that this cysteine, right, has to be a nucleophile, right? And it's going to be a nucleophile when it's in its deprotonated state, right? So it's got to be deprotonated, right? If cysteine has a normal pK of 8.14, right, and physiological pH is 7, right, pKa is greater than pH, right, it's probably going to be in its acidic form if I'm just at 8.14, right? So I need the pK of the cysteine to be less than 8.14, and actually less than 7 ideally, right? So it's in its basic form and its nucleophilic form, right? So I would say that for cysteine, I need it to be less than. Right? Does that logic make sense? Right? For the aspartate, right? I'm looking at this is quite acidic, right? So 3.71, one of the more acidic amino acids that we have, right? Actually, I think one of the most, possibly the most. So, but the thing is, right, this aspartate is acting as both an acid and a base, right? So normally at pK of 3.71, right, and pH 7, it's just going to be deprotonated the whole time, right? It's not really going to act as a base. It's going to be in a deprotonated form most of the time at like a massive ratio, right? So that's kind of weird, right? We need it to act as both, though. We need it to act as a base and act as an acid, right? So if I wanted to act as both a base and an acid, I would expect it to be a little bit higher than 3.71, maybe around 5, maybe 6. Maybe it is 7, right? That's a really high pKa for an aspartate, but it definitely should be higher, right? Because if in order for it to act as both an acid and a base, it needs to be able to accept that proton and deliver that proton. And if its pK is too low, it's just going to be mostly in its acidic form or in its basic form, right? Because it's going to be deprotonated, right? Does that make sense? So I'm expected to be greater than, right? Good? Okay. This question I actually lost points on because I was being an idiot. So, question 6, right, is talking about the gray circle, right? Within the active site shown above represents an amino acid residue that participates in hydrogen bonding with the phosphoryl group of the substrate and provides transition state stabilization. Predict an amino acid residue you'd expect in the gray circle. So, I was a clown and I said glutamine. I actually picked lysine and I was like, no, hydrogen bonding. It's gonna be glutamine. It's not glutamine, right? Now, I can see the argument why I said glutamine, right? I said, okay, well, if I put glutamine here, it can hydrogen bond with these minus charges. Lysine and arginine can do the exact same thing, right? Except they have an ionic interaction, right? So it's just objectively the better choice, right? So the fact that also, like, look at the orientation of the active site, right? I also look at that. So the fact that these two minus charges, right, are like right against this gray circle, right, tells me there's going to be some sort of ionic interaction going on there, right? And because of that, I can confidently say it's probably going to be a lysine or arginine, right? If these were like OHs instead, right, then I would probably say, okay, maybe it could be glutamine, or maybe it could be asparagine, or something like that, right? But because they're minus charged, right, it's going to be lysine or arginine. You could say histidine, but I think the issue with histidine is too close to physiological pH, right? So it's not a guarantee that's going to be always in a deprotonated or protonated form, right?
Wow.
Yeah, you want it to be protonated at all times, basically, right? And so histidine is close, right? And I think they actually gave partial credit for histidine. Did they give partial credit for it? Didn't say on the answer key. I'm pretty sure they did give partial credit for histidine, though. But lysine and arginine are better choices because they're farther away from physiological, right? You want it to be positive for the majority of the time, right? And histidine's around 50-50, 1 to 100, right? Something like that, right? Yes.
So why the lysine be a choice? Why not just arginine?
Because they're both positive at pH 7, right?
But why do you get both of those?
So can lysine. Lysine has 3 hydrogen bond donors, right?
I was just thinking like that eliminate Jews in this new lysine.
Yeah, lysine's got 3 of them, right? So lysine's got, in its protonated form, right? Protonated form, right? Remember protonated form, right? In its protonated form, lysine has 3 H's,
Right.
right? Arginine also has, I think, 3 H's, if I'm not mistaken, right? So their hydrogen bonding potential is pretty much the same,
Okay.
right?
Okay.
And there's no difference, right? The only difference is arginine is a higher pK, right? You can say lysine or arginine, by the way. You don't have to say both, right? You could say either one, right? I think the safer choice is arginine, but you can say lysine as well.
So then you can stabilize the charges.
Yeah, you're stabilizing the charges, right? So this is affecting this stabilization here, right? So I would say here, lysine or arginine. You can pick whichever one you want, right? Why would I say that? Because we need to stabilize the negative charges on the phosphates, and at physiological pH, the lysine or arginine is protonated. I spelled it wrong. Is protonated and is positively charged, which leads to an ionic interaction as well as hydrogen bonding. Right? Something like that. Right? Keep spelling arginine wrong. Okay. Make sense? Cool. Okay. This question should be a walk in the park, right? This question should be you look at it and you say, oh my goodness, thank goodness I've been saved, right? This is just, can you do addition, right? And can you cancel, right? Probably something you've done in Gen Chem before with Hess's law, right? So, this one shouldn't be that bad. I'm going to be honest, this page and this page are relatively free. The ones that are dumb are, this page can be weird, and this page made me want to cry when I first saw this exam. This page is horrible, okay? But we'll go ahead and take a look at this top one here. So, if you look at this, right, all you got to do here, right, is just do some addition. So, you're basically studying the catabolism of this disaccharide, right, and you find this bacteria strain contains this sucrose phosphorylase, right? It's an enzyme that does this thing where it phosphorylates sucrose, great. Or phosphorylates, it breaks apart sucrose into fructose and glucose, right? Which you should know the structures of, by the way. Cleavage of sucrose, right, is shown below. So we're using a phosphorylase, right, using an inorganic phosphate, right, similar to glycogen phosphorylase, right, if you remember that. And we're making this kind of weird thing here, right? So given the reactions below, what is the standard change in free energy of the phosphorylysis of sucrose, right? So the way that we do these, right, is we are looking for the product of one side to cancel with the reactant of the other, right? That is what we're looking for, right? And if we do not see that, right, we're going to have to do some sort of flipping here, right? And if you flip the reaction, you also flip the delta G, right? So let's go ahead and take a look, right, at what we have here. So if we take a look, so if I look at this, right, I can see glucose is on this side, and it's also on this side of reaction 1, right? Is there anything else that is shared? Water is shared and water is shared, right? See that, right? So all we got to do now is we just got to flip one of these reactions. In this case, I'm gonna flip the glucose one, right? So I'm gonna flip this guy here. I'm gonna flip this guy around, right? And if I flip that around, right, I have to multiply this by a negative, right? So that's gonna make this plus 12, right? I'm not gonna do that right now, but you get the idea, right? And so basically what's gonna happen is once I do this flipping and I do the canceling, right, this equation should match that, right? And we can go ahead and look at that, right? So if I flip this, right, my goodness, if I flip this, right, you can imagine that, actually I'll just draw it out, glucose, right, plus PI, right, makes glucose, I'm just going to say G1P, right, plus H2O, right? So I'm going to cross this out as well so I don't confuse it, right? So now if I look, right, glucose cancels with glucose, right? And water cancels with water. So now I'm left with, it's green here, sucrose, PI, G1P, and fructose. And if I look up at this equation, I've got fructose, G1P, PI, and sucrose. Notice how the sides of the equation have stayed the same, right? So fructose and G1P, right, are both on the right side of this arrow, right? And PI and sucrose are both on the left side of the arrow, right? So I'm looking for that equation to match, right? So now all I gotta do is just do a bit of math here, right? So I just gotta add these two values together now. So I flipped the second reaction, so I gotta do negative 27 kilojoules per mole plus, I'll do this the right way technically, it should be negative 12 technically, right? Right? That's technically how you do it, but like you could totally just write plus 12 and call it good, right? They're not going to dock you if you do that, right? I'm actually going to delete this so it doesn't look as cluttered, but make sure you write units again, right? This is going to be equal to negative 15 kilojoules per mole, right? And that sets you up for the next equation, right? Or the next question. So, the next question, right, is asking you to, you grow your strain in this concentration, right, with these substrates. What is the delta G of this reaction, right? So if you remember your equation, I highly suggest memorizing this, right? It's going to just be equal to the delta G. It's just going to be equal to the delta G, and prime is going to be equal to the delta G naught, right? And I don't remember if they put naught prime or whatever. It doesn't really matter, but I just copy it down from the equation sheet, right? Plus, and remember, this is important, right? The fact that they're simplifying it for you just makes life a little bit easier. So you just got to do 5 log of the products over the reactants, right? And for the products over the reactants, right, you just got to do a little bit of math here. So what are the products? The products are fructose and G1P. Fructose is 5, right? G1P is also 5, right? And also make sure the units are correct. We're using micromolars for all of these, right? So no problems there, right? And then the reactants are sucrose and phosphate, which is 100 times 10. Right? So now if I simplify, right, this is just going to be, this whole term here is just going to be 25 over 1,000, right? Which is the same thing as saying 0.025. Right?
Wait, were you recommend this doing 2.5 times 10 to the 1 over more times 10 to the
Sure, that's fine as well. That works too. Yeah, if you do it like that, that's totally fine. I know that 25 divided by 1,000 is 0.025, but like if you need to do the scientific notation, by all means do it. You're the one taking the exam, right? So if it helps you, go ahead and do it. Now you may be thinking, what the hell is this number? I don't know how to take the log of that. So how convenient they have that number down here for you.
Wait, what?
Right? So if you see a number that you have no idea how to take the log of, look at the log table. Right? Pretty sure you guys are given a log table if I'm not mistaken. If you get a number that is on the log table, there's 2 possibilities. 1, you're on the right track. 2, they've purposely made it so that you could make a mistake in the question and they've screwed you over. Right? Pray it's the first one, right? Usually you're probably right though, right? I mean, there's only really one way of doing these questions, right? And if you start going down a massive rabbit hole, you probably know that you've made a mistake somewhere, right? So I know that this is what I'm looking for, and I know this value is negative 1.6, right? That's there, right? So if I go back up, right, I know what this is, right, because I actually just calculated it up here, right? It's this negative 15, right? So now I just got to do a little bit of math. So negative 15, right, plus 5 times, and we just canceled out this whole log thing, right, which is just negative 1.6, right? So 5 times negative 1.6 is negative 8, right? So we're just going to be doing negative 15 plus negative 8, right? And that's going to be equal to negative 323 kilojoules per mole. That's our final answer. Does that make sense? Yeah? Cool? Yeah, these ones are a little bit easier, right? But yeah. Okay. This question's also not that bad. It just takes a little bit of how much of glycolysis do you remember, right? So, what would be the net yield of ATP if 1 mole of glucose 1-phosphate and 1 mole of fructose were converted into 2 moles of pyruvate? Okay, fill in the box to indicate how you determine the net yield. Okay, cool. So, glucose 1-phosphate to pyruvate, right? So glucose 1-phosphate, right? So every glucose we put in, right? We put 2 ATPs and we get 4 out, right? So we get a 2 net ATP, usually, right? That's because we need to use hexokinase, right? And PFK1 to add phosphates in the investment phase, right? If there is already a phosphate on glucose, I do not need to add a second phosphate. I don't need to use hexokinase to add another one, right? I can just mutase it and turn it into glucose 6-phosphate, right? So, if you look at this, glucose 1-phosphate, just use a mutase and you turn into glucose 6-phosphate, right? And now we're continuing to go, right? So, normally, under glycolysis, I use 2, I make 4. In this case, I only have to use 1 in PFK1 from phosphofructokinase 1, right? And I make 4 still, right? So my net is 3, right? So if I'm looking at this input, I'm only putting in 1, right? And my output is 4, right? That makes sense?
Would it be like glycogenesis as a G1B?
So this is most likely going to be a glycogenolysis, right? Because yeah, so glycogenolysis, right? You use glycogen phosphorylase, G1P, you use the mutase, and you change it into the G6P, right? Yep, yep.
So you said glycogenolysis is the pathway that we're using glucose phosphate?
Yes, this is specifically be in the muscle cell, right? Yeah. In the liver cell, it'll be a little bit different, right? You might use the glucose 1,6-bisphosphatase to release that phosphate and then send it up to what did I say? Glucose 6-phosphatase. Sorry, to get rid of the phosphate and then shoot it up into the blood, right? To go to the other organs, but yeah. So if we look at this now, we got fructose and pyruvate. So fructose has got nothing on it, right? So we're gonna definitely have to use 2 ATPs here, and we're gonna have to get 4 out, right? So if fructose is just an isomer, right? So there's really not gonna be much different there. But if I saw a phosphate on here, then maybe I would question a little bit, right? But there's no phosphates here, so I'm just gonna have to use 2 and 4, right? And so now we just got to use the net yield, right? And I don't think you really have to show your work too much here because you've already done your work here. Basically, right? I'm putting in 3, I'm getting out 8. My net's gonna be 5, right? Make sense? Cool. Here, so we got to compare the net yield of ATP from part C, right, to this new thing that we're making. So glucose molecule made a converted pyruvate. Maltose is converted to glucose by a hydrolytic enzyme, and it uses the following reaction. Okay, so they don't tell me anything about maltose other than the fact that it makes 2 glucose, which is more than enough information to do this question, right? Glucose, every glucose you use, right, uses 2 ATP and makes 4, right? If I put 2 glucose molecules in, right, I'm putting in 2 ATP for each one, and I'm making 4 for each one, right? So that means I'm putting in 4 total ATPs and making 8, right? Yep, okay. If we're putting in 4 and making 8, the net is going to be 4, right? So the net for this reaction is 4 ATP, right? And circle 1 or more is the yield more or less or the same as what you calculated in part C. Well, 4 is less than 5, right? So it's going to be less, right? And explain your reasoning. For this, explain your reasoning, I would say in part C, right, G1P already has a phosphate attached onto it. So we don't have to use hexokinase / glucokinase to add an extra phosphate in the investment phase, right? Because of that, we still get the 4 ATP from the payoff phase of G1P, G-pyruvate, but we make 3 net ATP due to not using an extra ATP in the investment phase, right? Just a little bit of repeating myself just to hammer the point home, right? I'm trying to make sure that they realize that I'm not an idiot, right? Because sometimes they read and they're just like, oh yeah, you didn't say it 5 times. So just keep this in mind. Sometimes they can be a bit annoying, and always fight for points back, right? If you said something, you definitely said it. So, okay. Now we get on to the part of the exam that this one can be a bit challenging, right? If you're even a little bit shaky on delta G and K, like the rates, this can easily trip you up. I think I actually did miss a decent amount of points in this question because I just was not thinking properly. And then this one is just mean. So we'll go over this, and we should have a lot of time to go over this. And I'm sure there's questions about this, but we'll see. So consider the reaction A to B, right? The delta G is negative 20. Okay, it is spontaneous, right? So negative 20 kilojoules per mole, more products than reactants, right? So my rate of products to reactants is much more skewed towards the product side, right? I start with 1 molar of compound A and find that after an overnight incubation at 25 degrees Celsius, you have 0.3 molar of compound B and 0.7 molar of compound A. Okay, so we've got a couple things here to take into account here. We could just go straight to these options and we can just go through them, but I do tend to try and make this a little bit easier on myself, and I try and say 0.7 molar and 0.3 molar right after a night of this incubation, right? So after I put these numbers in here, immediately a problem is jumping out to me, right? The fact that this is negative 20 and the products are not greater than the reactants tells me this reaction is not in equilibrium, right? If this reaction was in equilibrium, right, I would expect to see some sort of ratio that is closer to making this negative 20 kilojoules per mole. However, because you're not given anything about like the I guess you could figure out the KEQ, right? If they were to change up this question a little bit. But immediately, because there's not more products than reactants, right, I'm saying this is not equilibrium, right? So after this overnight incubation, we're not at equilibrium, right? Other than that, though, we just got to go through the questions and see if our prediction was right and they asked a question like that, right? So the reaction has reached equilibrium after an overnight incubation. No, right? It has not, right? It's not reached equilibrium because if it was at equilibrium, I need more products than reactants, and that is not what I have, right? I've got more reactants than products, right? The KEQ for the reaction is much greater than 1. That is true, right? Delta G is quite negative, right? So, and delta G, if you remember, negative RT ln KEQ, right? That is the equation for that. Since delta G is negative, right? K has to be greater than 1, right? The equilibrium rate of formation of compound B will be faster than the equilibrium rate of compound of A, right? What the heck? The rate of formation of compound B will be faster than the rate of compound A. No, because we're in steady state equilibrium, right? So the fact that we're in steady state equilibrium, right? It's just a case of remember what the definition of equilibrium is, right? Equilibrium, right, is when the rate of product formation is equal to the rate of reaction formation, right? That is what equilibrium is, right? And remember, rate is actually a completely separate term from equilibrium. Equilibrium tells you about the delta G, how spontaneous is this reaction. The rate tells you how fast it's going, right? So when at equilibrium, right, the rate of the forward reaction is equivalent to the rate of the backwards reaction, right? Does that make sense? This reaction might favor the products, right? That is true. However, if you make enough products, right, those products will eventually be able to go back in the other direction, right? So it's like if we do Le Chatelier's, right, and we have reactants to products, right? Even though the reaction is technically heavily skewed towards forming products, right? If we raise the products enough, right, Le Chatelier's will push it back to the other side, right? And at some point, those two values will be equal, right? That is what we're getting at here, right? Addition of an enzyme could shift the equilibrium. No, enzymes do not shift equilibriums, right? Enzymes, right? What do enzymes change? Transition state, so which is delta G double dagger, right? They change the activation energy, right? They do not change. If I have my reaction coordinate diagram, right? They change this, right? They do not change these two positions, right? Simple as, right? That's it, right? Starting the reaction with only 1 molar of compound B will lead to the formation of compound A. I sure hope so, right? So just because the reaction is spontaneous, right, and going towards products, does not mean that you're not going to have any reactants made, right? Equilibrium, right, is when you have, in this case, -20, right, which is some ratio of products to reactants, right? I don't know what that ratio exactly is, right? I'm sure you could do the math. I think in this case, it would probably be, you'd need something like log 4. So you'd have to do like, I don't know, 10,000 to 1, something like that, right? But there's still some reactant there, right? There's not just no reactant. So it will make reactant, right? It's very rare, right, that you have a reaction that just doesn't make any of its reactant, right? It's like practically impossible. How are you going to do equilibrium if you can't make your reactant, right? So that's how I would think about this, right? Any given reaction should form an equilibrium between its reactant and its product. And if there's an equilibrium between reactant and product, there's going to be some reactant and some product, even if there's more product than reactant or if there's more reactant than product, right? Does that make sense? Okay. Okay. Yeah, so this is a bit of a long one. Demonstrate my knowledge. Sure, man. Okay. Yeah, so there's a lot of knowledge that I have to use to get this question right, because this is a lot of points, and I actually don't remember how many points I missed on this. Yeah, anyways, I think the way I would recommend going through this is actually by column. So go like this. I think it's just a little bit easier because I think when I took the actual exam, I went across, and then I realized that I was basically trying to switch my brain from like gluconeogenesis to glycolysis, and then the glycogenolysis, and because those pathways are like so different. Like they're not so different, but they're like different enough from each other that like you start to mix up the enzymes in your head, and it just goes horribly wrong, right? So just pick one pathway and then go down the column, and you should be okay. Right? So, I've made videos about these, and I tried to hammer home what I thought was important about the glucagon, insulin pathway, whatever, right? Glucagon, starvation, right? Please make more sugar. And insulin is, I've eaten too much, I need to rest, please store the sugar, right? So, glycolysis, right, would be promoted by insulin, right? Not glucagon, right? And you put T or F in these boxes, don't you? Yeah, okay. So, glucagon, right, activates this pathway. That is false, right? Glucagon inhibits glycolysis to pyruvate, right? And it actually activates gluconeogenesis. So I know I said we're going to go down the column, right? But in this case, because I'm brained on this, right, I know that it doesn't do this. So I'm just going to say this is true, right? Fructose 2,6-bisphosphate is a potent inhibitor. Well, is it a potent inhibitor? It's not, right? So fructose 2,6-bisphosphate supercharges which enzyme in glycolysis? Which enzyme is activated? Which one? PFK what? 1. PFK1, right? So PFK1 promotes the forward reaction, right? From fructose 6-phosphate to fructose 1,6-bisphosphate, right? So this is also false, right? CO2 is released from glycolysis. Not that I can remember, right? I don't remember CO2 being released in glycolysis. So, I mean, if you're not sure, right, you can go through that process, right, and try and figure that out. That might take a little bit too long, though, right? Ideally, if you can remember what is produced and what is like being used, that makes it a little bit easier, right? Because you don't have to do all this like going through that process in your head, right? Even if you can remember like the glycolysis equation, that's good enough, right? So PI is a reactant or a product. Okay, is it a reactant or a product? And if so, what step?
6.
6. Okay, what is 6? What's the enzyme? What's the enzyme?
GATH3.
Yep, glyceraldehyde 3-phosphate dehydrogenase, right? So it is using it, and is it using it as a reactant or a product? Reactant, right? So it's using it as a reactant, right? So that's true. It says reactant or product, right? But they could easily ask, like, they could say as a product, right? And you have to say no, because it's not a product, right? It's a reactant in glycolysis, right? Uses biotin as a cofactor. Yeah, I don't think you guys have even talked about biotin as a cofactor for glycolysis. I think you've talked about biotin before, though, right? You've talked about biotin, right? So biotin is not involved in glycolysis, though, right? I talked about this in my lecture video, but if you see, there's two things. There's biotin and there's TPP, right? And you will see this in 441 again. So please remember this. Biotin is used in carboxylation reactions. So if you see a carboxylation reaction, you should be thinking biotin. Vitamin B7 is biotin, right? If you see a decarboxylation reaction, you should be thinking TPP, right? Or vitamin B1, right? So B1, TPP, B7, biotin. If you see a carboxylation, it's going to be B7, which is biotin. If you see a decarboxylation, it's going to be TPP, which is thiamine. Thiamine? Yeah. But there's no carboxylations in this, so I'm going to say it's false, right? There's nothing to do with that. NAD plus is produced. Is it produced or made in glycolysis?
Made.
It is in fact made, right? It is made in glycolysis, right? So it is not produced. It is made. Can occur in muscle cells. I sure hope it can occur in muscle cells, right? I sure hope we can do glycolysis in our muscle cells or we'd be in a really bad spot, right? So, yep.
Nutrition glycolysis?
Yeah, it is. But that question is asking AD plus. Read the question. Yeah. Yeah. So yeah. So you're right. NADH is produced, but the question is asking NAD plus, right? So yeah. Okay, now you can move on to gluconeogenesis, right? So gluconeogenesis, right? Usually it's going to be like if you see like a pathway question, it's going to be the opposite. But for things like CO2 release and stuff, you can't really just do the opposite, right? It's not really, it's just not really the most easy way to do things. So fructose, we already talked about glucagon, right? The gluconeogenesis pathway. So glucagon, right, promotes the gluconeogenic pathway. What cells does gluconeogenesis occur in? Liver or muscle? Liver. Does it occur in muscle cells?
No.
Okay, what enzyme do muscle cells not have? The main thing, huh? Did you say what enzyme do muscle cells not have that doesn't allow them to like export glucose out of their cells?
Phosphate.
What was it? Sorry.
Glucose 3-phosphate.
The glucose 6 phosphatase. Yeah. So yeah, right. So they don't have the glucose 6 phosphatase, right? The one that reverses step 1, right? So they can't just shoot glucose out, right? They can use it to make glycogen, right? Because they still have all those glycogen forming enzymes, right? But they cannot shoot glucose out of the cell, right? Because why would the muscle cell shoot glucose out, right? The muscle cell has to use glucose, right? The liver's job is to transport, right? So in this case, right, if we're doing gluconeogenesis, right, a fructose 2,6-bisphosphate, is that going to be an inhibitor or an activator of this pathway? Why is it an inhibitor?
This just this phosphate one reaction.
Yeah, so it would push pyruvate, right? And so in this case, it would activate, which enzyme would it activate in this pathway? Yep, fructose 1,6-bisphosphatase, right? So fructose 2,6-bisphosphate is an example of a reciprocal regulator, right? It activates fructose 1,6-bisphosphatase and inhibits PFK1, right? It's a reciprocal inhibitor or reciprocal regulator, right? So it is a potent inhibitor. That is in fact true. CO2 is released. Is that true or false? Why is it true?
It's about
Which one is that? Which enzymes are there?
It's like phosphorus.
Pyruvate carboxylase. So does pyruvate carboxylase release CO2?
Oh wait, they use the other group. And then when it goes to oxalic acid is what it is.
Pyruvate carboxylase turns it into oxaloacetate.
I mean decarbonate stuff.
What enzyme does the decarboxylation? Pep carboxykinase. Carboxykinase, right? What reactant do I use in that process? GTP. I'm also using ATP to do what?
Wait.
Activate what?
The CO2 adding to bottle.
Right, and the CO2 comes from what? Huh? Bicarbonate? It is bicarbonate. Comes from bicarb, right? You'll see this again in 441. Bicarb is how you actually get CO2, right? So you're using bicarb, you're attaching this ATP phosphate group on, right? You're attaching that to pyruvate to make oxaloacetate, right? And then you're using GTP, right? And guess what cofactor? TPP, right? TPP, vitamin B1, right? You're using as a cofactor to decarboxylate oxaloacetate, right? You get phosphenolpyruvate, right? So CO2 is in fact released from this, right? Phosphate is a reactant or a product, right? It has to be, right, because you have to do the reverse of step 6, right? So it has to be a reactant in this case, right? Actually, it has to be a product in this case, right? Because we're doing the reverse, right? That makes sense? Uses biotin as a cofactor. We're not using biotin here. We're not using biotin here, right? Or if I'm not mistaken, right? Unless, let me think about here. Sorry, wait. Pyruvate carboxylase uses it. Never mind. So, right, yeah. See, even though I forgot there, right? I was thinking about, is it a carboxylase? Is it not a carboxylase? Right? If it's a carboxylase, it uses biotin, right? So, carboxylase using biotin, right? It's going to be true, right? So you can catch yourself even if you make mistakes like that, right? NAD plus is produced. Yes, right? Because in this case, right, we're going the reverse of step 6, 7, right? No one make any jokes about that, please. Okay, thank you. Okay, so we're doing the reverse of those steps, right? And so if we're producing NADH, right, if we do the reverse, right, we're gonna make NAD plus, right? That's gonna be true. Can gluconeogenesis occur in muscle cells? No, it cannot, right? You cannot do gluconeogenesis in muscle cells, right? Why would the muscles do gluconeogenesis, right? That's something you can think about, right? They just wouldn't, right? Why would they do gluconeogenesis if they could just use that glucose to contract and do whatever they want, right? The only way you actually get glycogen stores, right, is you have so much glucose in your blood, right, that the amount of glucose you have kind of oversaturates, right, the hexokinase and glycogen synthase, right, to the point where you basically have to put some in storage, right? Because if you have to put some in storage, then you have to use those enzymes. But if you don't have to, then you're just not going to. You're just going to keep contracting, right? Good? 2 columns to go. So, glycogenolysis, right? So I think this is the more recent stuff for you guys, so this might be a little bit, but so we're going from glycogen to glucose 1-phosphate, right? So this is going to be the whole glycogen phosphorylase debranching enzyme, right? And then that debranching enzyme has a transferase mechanism and a glucosidase mechanism, right? 2 different mechanisms, right? The transferase is to move a large chunk of alpha-1,4 linkages, right, to the next chain, and the glucosidase is to cleave off that very last glucose, right, that is kind of hanging off of the branch. That is all it is, right? Glycogen phosphorylase is the one that cuts up the glucose chains, right, using phosphates, right? Phosphorylases, they use phosphates to cut, right? So, glucagon activates this pathway. Well, glucagon, right, is when you're under the starve state, right? And if you're under the starve state, right, you're going to want to produce more glucose, right? And if you're going to want to produce more glucose, right, that's where glycogenolysis would be used for, right? So this would be true. Is fructose 2,6-bisphosphate an inhibitor of this pathway? It's not involved. Fructose 2,6-bisphosphate is glycolysis, right? There is no involvement of fructose 2,6-bisphosphate in any other pathway really other than glycolysis, right? So that's false, right? Is CO2 released? Not really. There's no way a CO2 molecule can be released here, right? And if you'd be losing a carbon, then you wouldn't have glucose anymore, right? So there's really no way that CO2 can be released in this process, right? Is phosphate a reactant or a product? It's a reactant. For what enzyme?
Phosphorus.
Glycogen phosphorylase, right? Glycogen phosphorylase uses phosphate group, right, to cleave, right? So it's true there. Uses biotin as a cofactor. No carboxylations, right? There's no biotin, right? NAD plus is produced.
Yes. I love it.
Yeah, I trust your gut, right? If you don't remember there being NAD plus anywhere, probably wasn't produced, and you're right. There's no NAD plus produced in that pathway, right? Can occur in muscle cells. Can it occur in muscle cells?
Yes, so they have a store package.
No, they store glycogen, right? But it has to be oversaturated, right? There needs to be so much glucose that they force to store it. It would occur, right? It's true, right? You can do glycogenolysis, right? If you have those glucose stores, right, you need to be able to access them, right? There's no point in just storing it and then leaving it there and not doing anything with it, right? So you must have a way of breaking it down, right? These enzymes are definitely present in the muscle, right? And what I said before about like it's not going to really store that much glycogen. It's only really going to store glycogen if you have so much glucose in your blood, right? That it's kind of forced to go down that pathway, right? Because enzymes can saturate, right? You only have so many enzymes in your body, right? And if you, for example, saturate all the fructose 1,6 PFK1s, right? You can't really do that reaction anymore, right? So you might as well just store it somewhere else, right? Does that make sense what I'm talking about? Yeah? Okay. Now we're on to the last thing for fermentation, right? So fermentation is a bit different, but we're only looking at pyruvate to ethanol, right? So that's actually really important here. If we were looking at like from glucose to ethanol, then this changes a whole lot, right? We're only looking at pyruvate to ethanol, right? Very important, right? So if we remember the difference between pyruvate and ethanol, right? Pyruvate, right, is 3 carbons and ethanol is 2 carbons, right? So we've lost a carbon, right? Ethanol is also has an OH, it's an alcohol, right? And pyruvate is like a bunch of ketones, right? So there's probably a reduction reaction, right? Which involves NADH, right? Or NAD plus, right? I keep saying NADPH. That's later. You guys haven't done that yet. So I'm expecting things to do with all these things to do with NAD plus and stuff. There's going to be some, I have to like think about those a little bit more, right? So glucagon activates this pathway. Well, so fermentation, right? Fermentation is going from pyruvate to ethanol, right? So you would have had to go through glycolysis, right? You would have had to go through this whole process to make make ethanol, right? So by that logic, you can say it's false because glucagon would do the reverse, right? Glucagon would actually go from pyruvate back or from ethanol back into pyruvate, right? So that's definitely false, right? Fructose 2,6-bisphosphate is a potent inhibitor. Same logic as glucagon, right? In this case, fructose 2,6-bisphosphate has no effect, right, on ethanol fermentation, right, going from pyruvate to ethanol. Even if it did, though, because we're going in the forward direction, it'd probably be activating even if it did have an effect on it, right? Does that make sense? So even if you don't have the knowledge of whether or not it actually affects it, you can kind of intuit your way through that, right? So false. CO2 is released, right? True or false?
True.
True. Why is it true?
Lost.
Loss of a carbon, right? So generally speaking, we have loss of a carbon, right? It's most likely going to be a CO2 release. We'll see later on when you guys do pentose phosphate pathway, there's some kind of shenanigans you can do there where it's not quite a CO2 release, but it's similar, right? But in this case, right, there is in fact a CO2 release, right? Because we're going from, oh my goodness, I forgot my charger. No, I didn't. I just didn't plug it in. There we go. Okay. Okay, cool. So it is true, right? CO2 is in fact released, right? Phosphate is a reactant or a product, specifically from pyruvate to ethanol. Is there any case that we phosphorylate the pyruvate when we're going to ethanol? No. Yeah, there's no case where we phosphorylate the pyruvate, right? So this is going to be false, right? Remember, we're only talking about pyruvate to ethanol. If we were going from glucose to ethanol, then I would have said that sure, there is, because remember step 6, right? But we're not doing that. We're going from pyruvate to ethanol, right? All that happens from pyruvate to ethanol is a decarboxylation followed by a reduction, right? Does it use biotin as a cofactor?
No.
No, because there's no carboxylation reactions, right? There's a decarboxylation reaction which uses what cofactor? TPP, right? I don't know. Do you guys cover TPP? I think I saw it. I did see it in your lecture slides when I was doing the reviews, so it was in there. But there's not really that many TPP reactions yet. When you guys do pyruvate dehydrogenase for exam 3, it will show up again. Both of them will show up actually. Biotin doesn't actually. TPP does, and then lipoic acid does, but it's a separate thing. NAD plus, is it produced? It is produced, right? Because we're reducing pyruvate, right? We're reducing this. It actually technically goes from pyruvate decarboxylate into acetaldehyde, right? Acetaldehyde, right? And then acetaldehyde is reduced into to the ethanol, right? So NAD plus, it is in fact produced, right? Can this occur in muscle cells? It cannot, right? We cannot do fermentation, right? If we could do fermentation, we'd have a lot of alcohol in our system, we'd all be drunk. So, so no, right? Yeah, no. So we can do lactic acid buildup though. So if they do ask a lactic acid question, right, they can do that, right? So we can do lactic acid buildup, right? But we can't do fermentation, right? That's what yeast are for, right? That's why we can't make alcohol with our own bodies, right? Because we don't have fermentation, right? But congratulations, that is the exam, and we are done. Any questions about the exam or about any of the content that you guys are covering for the test? Yeah.
For Louis 2,
Okay.
that's the one that's for liver.
Yeah.
When in our notes said that it has a high capacity for glucose, is that just that the cell store a lot of glucose?
Yeah, I think what that's saying is that it can store a lot of glucose, and generally speaking, when they talk about capacity, usually it means that I don't want to say Vmax, but like the rate of transport is kind of quick, right? Which is different from the binding affinity, right? So that's like it's like Kcat, right, versus Km, right? It's quick to like once it binds, it's quick to pull it in, but it's not quick to bind in the first place, right? So it can bind a lot, right, and it can transport fast, but it doesn't really it doesn't really bind that often. What that means, right? That makes sense.
So that's why it's like practice.
Yeah. I mean, it's just a case of like if you do have like no worries. If you do have a lot of glucose, right, and like you're oversaturating all of your cells, right, you're gonna want to absorb
Right.
all of that glucose in your liver, right, because you want to store it, right. So it's gonna have a high like Vmax in the sense that it's gonna need to quickly be able to take that glucose and store it, right. But it has to have a lower Km or a higher Km, sorry, because you don't want it to just take all the small amounts of glucose that are available. Only when there's high amount of glucose, right? So high capacity means we have a high Vmax and you have a decent amount of binding sites for the glucose, right? And they're all independent of each other, right? Usually, right? Right? Yep. Any other questions?
For question one,
Uh huh.
E.
1E. Yep. 1E. Yep.
What was your like kind of like thought process of that? Because I was kind of I don't know why.
For this one?
Yeah.
Yeah. So this one's a bit weird, but for if you're looking at the substrate, right, at 6 micromolar, and we're looking at it in the absence of the inhibitor compared to the presence of the inhibitor, right? So we're looking at curve A, right, and curve B, right? And if we look at 6 micromolar, right, we can see that the V naught for A is quite a bit higher than B, right? Which means that the rate we're forming, because what V naught is, right? V naught is the rate at which we're forming the enzyme product, right? It's the rate at which we're forming the product, basically, right? So
It's forming that's
A is forming it faster, right? So because A is forming enzyme substrate quicker, right? Because in order to get to enzyme product faster, you have to form enzyme substrate faster, right?
okay, so it forms faster, it forms more.
Generally speaking, yes. Yeah.
Okay, so that's weird.
Yeah, that's why I put higher. Yeah.
And then there's another one for literally the question right after that.
This one? Or F. Okay, yeah.
So where do you get that 5 micromolar?
This one?
Was I was pharmacy here.
Yeah, yeah, no worries.
That's so start.
No, you're fine, you're fine. So yeah, so basically, right, the V max, right, is
Is that the 1/2 Vmax?
yes. Well, no, that's different, right? So this because we're doing an uncompetitive inhibitor, right?
Oh, is that the one that like with the A or something like makes it?
Yeah, so it divides by alpha, right? But in this case, right, curve C it's asking about, right? Specifically asking about curve C. Curve C is this one.
Oh, and it looks like it like.
It looks like it plateaus around 5,
Okay,
right? So that's how you can kind of say it's 5. The Vmax for this enzyme is now 5,
okay, so
right?
that was. Can you go back to that? Please?
Yeah, yeah. Just realized I